In December 2025, a research firm called Tech Insights took apart a brand new Chinese phone, the Huawei Mate 80 Pro Max, piece by piece, just to look at one tiny chip inside it. That chip, the Kirin 9030, is smaller than a fingernail. But when the engineers finished testing it, they said something that sent a jolt through boardrooms in California. They said this tiny chip was the most advanced piece of silicon China had ever built on its own, with no help from the machines America had spent years trying to block. Nobody in Washington expected that sentence to be true this soon. Here's the part that makes it stranger. The machines everyone agreed China was not allowed to have, and the machines almost every expert said were absolutely required to build a chip like this, were nowhere near that factory floor. China built this chip anyway, using tools that were supposed to be one full generation behind. And by the end of this video, you will understand exactly how they pulled that off, why it terrifies American chip companies more than any missile test ever could, and why the fight over these tiny slices of silicon might quietly decide who leads the world for the next 50 years. Before we go further, if the idea of a hidden tech war being fought inside chips smaller than a grain of rice is the kind of thing that keeps your brain busy at 2 in the morning, you will probably enjoy where this channel goes next. Sticking around and subscribing just means you will not miss the next one. And if this topic genuinely grabs you the way it grabbed me while researching it, that's really the only reason to bother. To understand why this moment is such a big deal, you need to understand just how hard it is supposed to be for anyone to do this, let alone a company locked out of the best tools on the planet. Making an advanced computer chip is one of the most difficult manufacturing feats humans have ever attempted. Harder in some ways than building a rocket, because a rocket does not need to work at a scale 1,000 times smaller than a human hair. A single chip factory, called a fab, can cost more than $20 billion to build from the ground up. Inside that factory, machines carve patterns onto thin disks of silicon called wafers, and those patterns are smaller than a strand of human DNA. One speck of dust, one tiny vibration from a truck driving past outside, one fraction of a degree of extra heat, and the whole batch of chips can be ruined. That is the level of precision we are talking about before we even get to the part that makes China's situation so much harder. For decades, one company held the keys to the most advanced level of this process, and almost nobody outside the semiconductor industry has ever heard its name. It is a Dutch company called ASML, and it builds machines called EUV lithography machines. EUV standing for extreme ultraviolet, which is just a very short, very powerful kind of light. These machines use that light to draw circuit patterns so fine that a single fingernail-sized chip can hold tens of billions of tiny switches called transistors. Think of a transistor as a light switch smaller than a virus, and a modern chip has tens of billions of them, all wired together, all working in perfect sync. There is no other company on Earth that can build these EUV machines at the same level ASML does. Not in the United States, not in Japan, not in China. And starting in 2019, and tightening hard in the years after, the United States government pushed the Netherlands, ASML's home country, to make absolutely sure China could never buy one of these machines, no matter how much money Chinese companies offered. That should have ended the story right there. Without EUV machines, most experts believe China would get permanently stuck at older, clunkier chip technology, years behind Taiwan and the United States, unable to build the powerful processors needed for smartphones, artificial intelligence, and modern military systems. For a while, it genuinely looked like they were right. Chip experts wrote articles explaining in confident detail why this was basically game over for China's most advanced ambitions. So how did a Chinese company just produce what independent Western analysts are calling the most advanced chip China has ever made, using machines everyone agreed were not good enough for the job? The answer is one of the strangest engineering workarounds in modern industry, and once you understand it, you will never look at a computer chip the same way again. Picture a professional muralist trying to paint an incredibly detailed portrait on a wall, the kind with fine eyelashes and tiny highlights in the eyes. Now imagine that muralist is only allowed to use a paintbrush that is far too thick for that level of detail, the kind you would normally use for painting a fence, not a face. A skilled painter with the right thin brush could finish that portrait in one careful pass. But if that thin brush is banned entirely, a clever and stubborn painter can still get close to the same result by painting the same wall over and over, layer after layer, shifting a stencil slightly each time, letting the fine details slowly emerge from repetition instead of precision. That is essentially what SMIC, China's largest chipmaker, has been doing with its most advanced chips. SMIC does not have ASML's cutting-edge EUV machines sitting in its factories. Instead, it works with older machines, called deep ultraviolet, or DUV, lithography tools, the kind normally used to build chips a full generation or two behind the cutting edge. But by running the same silicon wafer through the machine multiple times, exposing it, shifting the pattern slightly, exposing it again, sometimes 4 or 5 separate passes for a pattern that would normally take just one pass on a proper EUV machine, SMIC has managed to fake its way to what is called a 7-nanometer chip. It is slower. It is far more expensive per chip. But according to multiple independent teardown reports, it genuinely works. Here is the part that should worry American chip executives even more than the chip itself. Huawei, the tech giant that got hit hardest by US sanctions back in 2019, has not just been buying these chips off the shelf. It has reportedly been co-designing them, working shoulder to shoulder with SMIC's own process engineers to squeeze every last drop of performance out of a manufacturing method that was never meant to reach this far. Huawei's own AI chip, called the Ascend, and its phone processor, the Kirin, are both now being produced this way, in close collaboration, rather than a simple customer and supplier relationship. And that raises the next obvious question. If the multiple pass trick works, why hasn't every chip company on Earth just been doing this the whole time, sanctions or not, and saving themselves $20 billion on EUV machines? The honest answer is that this shortcut comes with brutal, unforgiving costs, and understanding those costs is the key to understanding the real state of this race, not just the exciting headline version of it. Every extra pass through the lithography machine adds time, adds cost, and adds risk, all three at once. Each additional pass is another chance for the pattern to land even slightly out of alignment, off by a distance smaller than a virus. And when that happens, the entire chip becomes unusable scrap. So while SMIC can technically produce these advanced chips using this brute force method, a huge share of every batch comes out broken, and that failure rate is not a small side detail. It is the whole story hiding underneath the exciting headline. Industry reports place the yield rate, meaning the percentage of chips that actually work after manufacturing, for Huawei's newest Ascend 910C chip somewhere between 20 and 40%. Compare that to the industry gold standard, where top factories in Taiwan routinely achieve yields well above 90% for their mature, well-understood processes. That gap is enormous, almost hard to picture. It means for every 10 advanced Chinese AI chips that come off the production line, as many as 8 of them might end up defective, thrown in the scrap bin after already burning through the same expensive silicon, chemicals, and machine time as the 2 chips that actually worked. So is this a genuine breakthrough, or is it an extremely expensive party trick, propped up entirely by government money and pride? The honest answer sits somewhere in between those two extremes, and that middle ground is exactly what makes this story more interesting than either the panic headlines or the dismissive ones. Let's look at what is actually verified, on the record, from real financial filings and real independent reporting, because vague claims are cheap, and this story deserves better than vague claims. SMIC is a publicly listed company, which means its spending shows up in real financial filings that anyone with an internet connection can check for themselves. In 2025, SMIC spent $8.1 billion on capital expenditure alone, a jump of more than 10.5% compared with the year before. For 2026, that spending is projected to stay just as aggressive, reportedly exceeding 20% of the company's audited net assets, according to filings with the Hong Kong Stock Exchange. For a company running on a net profit margin of only around 6%, that kind of spending is not normal business behavior at all. That is a company plowing almost every dollar of profit it makes, plus a significant amount of borrowed money, straight back into expansion. That is the kind of spending pattern you usually only see when a national government is standing directly behind the checkbook, treating a private company's balance sheet as a matter of state strategy rather than shareholder returns. And China's government is standing behind it, openly. Beijing has poured state-directed investment into SMIC for years, specifically to build a domestic chip industry that does not depend on the United States or its allies for anything critical. This is not primarily about beating TSMC on cost or efficiency in a fair, open marketplace. It is about guaranteeing that no matter what sanctions come next, no matter how tight the export controls get, China can still build the chips its economy, its AI ambitions, and its military systems need to function. That single strategic goal explains almost everything else in this story, including why a company would keep making chips with a 20 to 40% failure rate instead of simply waiting years for better technology to arrive on its own. Meanwhile, on the equipment side of this race, a newer and much lesser-known company called Carrier has been aggressively building out Chinese-made chipmaking tools, aiming for what industry watchers are calling a Huawei-style full-stack ecosystem, meaning a chip supply chain with no foreign parts required at any single stage, from raw silicon all the way to a finished processor. If that sounds like an enormous undertaking, it is because it genuinely is. But catching up to 7-nanometer chips without EUV machines sounded impossible too, and here we are, watching it happen in real time. There is one more piece of the mechanism worth understanding, because it explains why this workaround could not have happened 10 years ago, even if someone had thought of it. Multiple patterning, the technical name for this repeated exposure trick, requires an almost inhuman level of control over alignment between each pass. Imagine printing a color magazine photo by running the same page through a printer 4 separate times, once for each ink color, and needing every single pass to line up with the last one within a margin smaller than a single grain of pollen. Miss that alignment even slightly, and the picture turns into a smeared, unreadable mess. Chip engineers call this overlay accuracy, and achieving it on older DUV machines that were never designed for this kind of repeated precision work took years of software tuning, custom calibration routines, and a level of manufacturing discipline that most Western analysts assumed Chinese fabs simply did not yet possess. The fact that SMIC has pushed overlay accuracy far enough to make 7-nanometer chips work at all, even at a rough 20 to 40% yield, tells you the software and process engineering side of China's chip industry has matured just as fast as the hardware side, maybe faster. None of this matters if it stays trapped inside a lab or a spreadsheet somewhere in Shanghai. So let's look at where this is actually showing up in the real world right now. Not someday, not hypothetically, but today. SMIC's 7-nanometer production, the kind used inside Huawei's Ascend chips, is currently estimated at somewhere between 45,000 and 60,000 wafers per month. Each of those wafers can be cut into hundreds of individual chips, depending on exactly how the chip is designed and laid out. Huawei has publicly signaled plans to roughly double its output of the Ascend AI chip during 2026, with internal targets reportedly aiming for as many as 1.6 million individual chip units, what engineers call die, by the end of the year. If Huawei actually hits that number, some analysts believe it would represent a real technical turning point, not just for Huawei's own AI ambitions, but for Beijing's much broader goal of never again depending on foreign chip supplies for its most critical technology, from smartphones to fighter jets to AI data centers. There is a second company worth watching closely here as well, one that rarely makes headlines outside industry newsletters. Huahong, China's second-largest chip foundry, has spent most of its history making simpler, mature chips for cars and industrial machines, nothing close to advanced AI processors. But as of early 2026, Huahong's subsidiary, a company called Huali, is reportedly preparing its own 7-nanometer production line at a plant in Shanghai, with direct support from both Huawei and C-Carrier. It is starting small, aiming for just a few thousand wafers a month by the end of the year, tiny compared to SMIC's much larger output. But if that line succeeds, it means China would have a second independent company capable of producing advanced AI-grade chips, which spreads out the risk and the capacity across the whole ecosystem in a way that makes it far harder for any single new round of sanctions to slow the entire industry down at once. What happens when one bottleneck turns into 2 separate supply chains, both racing toward the same finish line? It's worth putting some real numbers around China's overall chip market too, because the scale here is easy to underestimate. Industry researchers at Mordor Intelligence estimate the entire Chinese semiconductor device market was worth roughly $233 billion in 2026, and they project it will grow to more than $332 billion by 2031, a compound annual growth rate above 7%. Communication-related chips, the kind found in phones and network equipment, already make up about a third of that market, while chips built specifically for artificial intelligence applications are projected to grow even faster through the end of the decade. This is not a niche side project buried inside a state 5-year plan. It is one of the largest industrial bets any government has placed on a single technology in modern history. Even with all that spending, SMIC's global position tells a more complicated story than pure momentum alone. Despite years of heavy internal investment from 2021 through 2024, SMIC has maintained a relatively stable 5 to 6% share of the entire global foundry market, according to industry tracking. That is a useful reality check. SMIC is not clawing away customers from TSMC on the open world market. It has instead become something closer to a national champion, a company whose real customer base is increasingly just China itself, building the domestic chips China's own tech giants are legally and strategically required to buy. Step back from the factory floor for a moment, and you start to see why this story is so much bigger than one chip, one phone, or even one company. Some analysts have run the math on what happens if SMIC devoted its entire advanced chip manufacturing capacity purely to producing Huawei's Ascend line. The theoretical answer that comes out is tens of millions of Ascend chips per year by around 2027. For comparison, NVIDIA, the American company that currently dominates the global AI chip market by a wide margin, sold an estimated 4.5 million AI processors globally across all of 2025. That single comparison is what is quietly rattling American chip executives right now, more than any single new chip announcement ever could. Not because China has already caught up, because by almost every serious measure it clearly has not, but because the gap that used to look like a permanent, unbridgeable wall now looks like a steep hill that is genuinely being climbed. Slowly, expensively, imperfectly, but steadily, using tools that were specifically designed to make climbing it impossible. If a country can build tens of millions of AI chips a year using machines that are a full generation behind the cutting edge, what happens if it eventually finds a way to get its hands on something closer to the real thing? Think about what changes for ordinary industries once a country can reliably build tens of millions of AI chips a year, even at a rougher, more expensive standard than the best in the world. Hospitals running AI diagnosis tools, factories running AI-powered quality control cameras, self-driving trucks, weather models trying to predict the next flood, all of it eventually needs a steady, dependable stream of chips. A country that can build its own supply, even an imperfect one, is a country that cannot be starved out of the AI race by another nation simply refusing to sell it hardware. That kind of independence changes the leverage in every future negotiation, every future dispute, every future crisis. This is where the story connects to something much bigger than semiconductors, bigger than any one phone or any one company's quarterly earnings. Whoever controls access to the most advanced AI chips effectively controls the pace of progress across almost every other field that increasingly depends on artificial intelligence, from military targeting systems to drug discovery to weather prediction to economic forecasting. That is precisely why the United States did not just quietly discourage chip sales to China. It built an entire wall of export controls specifically engineered to prevent this exact outcome from ever happening. And that wall is being climbed anyway, brick by brick, one expensive and imperfect workaround at a time. Every headline about a new Chinese chip is really a small update on how tall that wall still is, and how quickly the climbing is happening. So what happens if that climb does not slow down over the next few years, the way so many analysts confidently predicted it would? Now, it would be dishonest, and honestly a little insulting to your intelligence, to end this video making it sound like China has already won the chip race outright. It is not, and the gap that remains is real, expensive, and in some important ways getting harder to close rather than easier. Let's talk about that part honestly, because a channel that only ever tells you the exciting half of the story is not a channel worth trusting with the rest of your time. The yield problem is not going away anytime soon, and it is not a minor footnote. A 20 to 40% success rate is not just an awkward number tucked away in a spreadsheet. It is a permanent tax applied to every single chip SMIC and Huawei produce using this workaround method. Every broken, discarded chip still costs the same expensive silicon wafer, the same precious machine time, the same electricity and highly skilled labor as a working one. That means Chinese advanced chips are, and will likely remain for years to come, significantly more expensive to produce per working unit than equivalent chips manufactured in Taiwan using proper EUV machines. That extra cost has to be absorbed somewhere, either by the Chinese government, by Chinese companies quietly charging more, or by cutting corners in some other part of the process. There is also a hard physical ceiling to worry about. Experts widely agree that this multiple-pass DUV workaround starts to fundamentally break down below 5 nanometers. At that scale, the patterns become so unbelievably fine that stacking several imperfect passes on top of one another stops producing usable chips at all, no matter how many extra passes you throw at the problem. SMIC has reportedly entered early pilot production runs for a 5-nanometer process, aimed at mass production sometime in 2026, but industry watchers remain openly skeptical about whether that process can ever become genuinely commercially competitive without real EUV equipment behind it. Getting down to 3 nanometers or smaller, the range where the newest iPhones and the very top-tier AI training chips already live, may require breakthroughs China simply does not have in hand yet. That includes reported early-stage research into unconventional carbon-based transistor designs, which sound genuinely futuristic on paper, but remain years away from any kind of proven, reliable mass production line. Then there is the memory problem, which almost nobody outside the industry talks about, even though it might matter just as much as the processor itself. Advanced AI chips do not work alone. They need to be paired with extremely fast memory chips called HBM, short for high bandwidth memory. And right now, China's domestic HBM production is still playing catch-up, with Huawei reportedly relying partly on existing stockpiles of memory chips bought from South Korean suppliers before the sanctions tightened even further. Without a steady, high-quality, fully domestic memory supply, even a technically perfect logic chip is still only half of the finished puzzle. There is also a talent and equipment bottleneck that money alone cannot instantly fix. Building machines as precise as ASML's took that single company literally decades of accumulated engineering knowledge, patents, and supplier relationships spread across dozens of countries, from special mirrors ground in Germany to light sources built in San Diego. SI Carrier and other Chinese equipment makers are trying to compress that decades-long learning curve into a handful of years, which is an extraordinary goal, but rebuilding an entire specialized global supply chain from scratch, essentially in isolation, is one of the hardest industrial challenges any nation has ever set for itself, and history offers very few examples of it happening quickly. So while the progress here is absolutely real, and while it is happening noticeably faster than almost anyone sitting in Washington predicted just 3 years ago, this is not a finished race with a clear winner yet. It is a very expensive, very determined climb up a hill that keeps getting steeper the higher you go, with real setbacks mixed in among the real wins. It also helps to remember why the United States built this wall in the first place, since it is easy to lose that context in the middle of all these technical details. American chip export rules were never really about protecting NVIDIA's or Intel's sales figures. They were built on the belief that keeping the most advanced chips out of Chinese hands would buy the United States and its allies years, maybe a decade or more, of breathing room in AI development, enough time to build a commanding lead before China could catch up on its own. That was the entire bet behind the strategy. What the Kirin 9030 teardown suggests is that the buying time part of that bet is working far less cleanly than planned, and that the years of breathing room policymakers were counting on may already be shrinking faster than anyone in Washington wants to admit publicly. So here is where all of this actually leaves us. A Chinese company, deliberately cut off from the world's best chip-making machines, has managed to build the most advanced chip China has ever produced, not through some secret hidden breakthrough, but by brute forcing an old machine to do a newer machine's job, over and over at enormous financial cost, with a huge number of failures scattered along the way. It is not full technological parity with the West. It might not be for years, possibly much longer. But it is undeniable proof that the wall the United States built to slow China down has a real crack running through it, and that crack appears to be getting wider every quarter that SMIC posts another record-breaking capital expenditure number. Whether that crack eventually splits the wall wide open or gets sealed shut again by the next round of tighter export rules is genuinely still an open question, and it is one that engineers, analysts, and governments on both sides are watching closely right now. If you have made it this far, here is a real question for you, not a rhetorical throwaway line. Do you think export controls like the ones the United States placed on ASML's machines actually work in the long run? Or do they mostly just force the country being targeted to get more creative and more self-reliant, faster than it ever would have otherwise? Type your honest answer down in the comments. I genuinely want to see where people land on this one. And if this kind of deep dive into the tech war that nobody seems to be talking about enough is useful to you, hitting subscribe and turning on notifications means you will catch the next one the moment it goes live.